Hi, I'm Dr. John Coimber-Walsh, a software development engineer at Amazon, and in this video, I'm going to be showing you a new technique we've developed for optimizing test runtimes called Fast Test Impact Analysis. Automated testing is an integral component of continuous integration and continuous delivery pipelines by acting as a gating mechanism to ensure that any incoming source changes by contributors do not break new or existing functionality. The duration of automated testing is affected not just by the number of tests to run, but also the frequency of contributions coming into the codebase. Long durations of automated testing are an impediment to adding new features and fixing important bugs. One technique for reducing the duration of automated testing is test impact analysis. This technique works on the assumption that, for a given set of incoming source changes, we are only required to run the relevant subset of tests that cover those source changes. It therefore stands to reason that any tests not covering those source changes are incapable of detecting new bugs and regressions. As this technique uses coverage data to determine which test targets cover which production sources, we need some means of instrumentation to generate this coverage for each test target in the codebase. Here is a simplified cycle of test impact analysis as it runs in automated testing. Before we start, we run an initial seed of all test targets to generate their coverage data. Once this seed is in place, each run of automating testing triggers the following cycle. First, we draw from our existing coverage data to select and prioritize the relevant subset of tests for the incoming changes. Then, we run those selected tests with instrumentation. Once those tests have completed, we take the coverage data that was generated for them and update our existing coverage data with the latest snapshot. This cycle of selecting, running, and updating allows each subsequent run of automated testing to use the most up-to-date coverage data for its test selection. This is incredibly important for test impact analysis because if the data drifts and becomes stale, then we can no longer be confident in our ability to select the relevant subset of tests for a given set of changes based on the existing coverage data. Let's look at the test selection in a bit more detail. This white circle represents all of the test targets in the codebase. Without test impact analysis, each time a contributor submits some changes for the codebase, we trigger a cycle of automated testing, which in turn runs all of the tests in this circle. Now let's look at how test selection works with test impact analysis. By analyzing the incoming set of source changes and cross-referencing them with the existing coverage data, we have determined the relevant subset of tests to be those confined in the red circle. Note that this red circle is significantly smaller than the white circle. Therefore, for this run of automated testing for this set of incoming source changes, we should expect to see a significant reduction in duration compared to running all of the tests in the white circle. The instrumentation we use for the test impact analysis framework is a tool called OpenCPP Coverage. We chose this tool for the following reasons. Firstly, it's open source, which allows us to modify its functionality to our needs. Secondly, it's free for commercial use, which is critical for a free and open source game engine such as O3DE. Thirdly, it's not tied to any specific toolchain, so we don't have to use any particular compiler in order to use this tool. And finally, it's available on the Windows platform. The way that OpenCPP Coverage generates its coverage data is as clever as it is simple. It launches the test binary as a child process and attaches itself as the debugger. It then enumerates all of the source files in the PDB file associated with that binary, as well as any PDB files of any child processes and dynamic link libraries linked at runtime. It then adds a breakpoint to every executable statement in all of those binaries before running the test binary and recording which breakpoints are hit. Once the test binary has completed its run, it cross-references all of the breakpoints that were hit and associates them with lines in source files to generate line-by-line coverage for every single source file covered by that test binary. In this graph, we can see the duration required to place the breakpoints for 5 different test targets. Note that the duration required to place the breakpoint scales almost linearly with the number of lines covered by those test targets. In the worst case, we can say it takes over 18 seconds to place all of the breakpoints for a particular test target before we even start the test run. Not only is there a performance penalty to placing the breakpoints, there's also a further performance penalty for actually running the test and hitting those breakpoints. The harsh reality is that OpenCPP coverage is very slow at generating its coverage data. This isn't really a criticism of OpenCPP coverage because it was not developed with test impact analysis in mind. It was developed simply to generate coverage data for given test targets, at which it does an excellent job. However, the pilot test binary which we chose to measure the performances of OpenCPP coverage was 38 times slower than running it without OpenCPP coverage. As we saw in the previous graph, the performance degrades linearly with the number of sources just for the breakpoint placing. Therefore, the bottleneck is in the breakpoint placing and breakpoint triggering. As integration tests typically cover many production sources, this degrading of performance in line with the number of possible executable lines in the test binary where we need to place the breakpoints makes it prohibitively expensive to use in test impact analysis. No matter how much we try and make the numbers work, there is no scenario where a slowdown of 38 times or more can be useful in test impact analysis, where the entire point is to reduce the duration of automated testing, not increase it. This brings us to a technique we developed called fast test impact analysis. With fast test impact analysis, rather than attempting to determine the true line-by-line coverage of a given test target, we instead generate an approximation that is the superset of the actual coverage. This allows us to be as inexact as we need with our approximation in order to speed up our test targets run with instrumentation such that they can be used in test impact analysis. This approach works so long as the approximation is always a superset of the actual coverage. This does imply that during our test selection, we may select tests that do not cover a given set of source changes coming into the codebase. However, so long as the cost of running those wasted tests is exceeded by the savings made by running only the subset of tests selected in the approximation, then we can still deliver performance gains to automated testings. Let's revisit our test selection, but using fast test impact analysis. As with before, the white circle represents all of the tests in the codebase, and the red circle represents the actual relevant subset of tests for a given set of incoming source changes. However, this time we have the addition of a yellow circle. This yellow circle represents the relevant subset of tests selected for the same set of incoming source changes, but using the approximation of test coverage. Notice that the approximation contains the actual relevant subset of tests. Therefore, all of the tests in the yellow circle but not the red circle are wasted tests drawn in by the test selection using fast test impact analysis. It's important to note that although the yellow circle is larger than the red circle, the yellow circle is still considerably smaller than the white circle. Even when we draw in wasted tests that do not cover the incoming set of source changes, the net result is still a reduction in duration of automated testing. Now let's revisit how the instrumentation works using fast test impact analysis compared to using regular OpenCPP coverage. The steps are broadly the same. The key difference, however, is rather than adding the breakpoints and recording which breakpoints are hit, we instead simply enumerate all of the source files of the test target binary and any child processes and shared libraries linked at runtime. For debug builds, this effectively gives us all of the source files used to generate the test target binary and any compile time and runtime dependencies used by that binary. Whilst it may seem at first glance that the amount of wasted tests drawn in by the test selector of fast test impact analysis would make the entire exercise pointless, you have to keep in mind that for a codebase as large as O3DE, with its hundreds of test targets, tens of thousands of source files, and millions of potentially executable lines of codes, and therefore potential places for putting breakpoints, the performance benefits still significantly reduce the duration of automated testing. You might be thinking this is a lot of work to determine the sources used to build a given test binary, as well as any of its compile time and runtime dependencies. You may also be thinking there are already existing alternatives to test impact analysis that simply use static analysis of the build system. With these approaches, for a given test target, they walk through the dependency graph of that test target in order to determine which sources belong to which production targets that are dependees of that test target. However, these approaches are incapable of determining runtime dependencies of not just the test target, but any other build targets that that test target depends on. For example, if that test target or any dependent build targets launch any child processes or link to any shared libraries at runtime, static analysis of the build system will be incapable of enumerating those dependencies and thus inferring the coverage from those dependencies. The performance of using this modified instrumentation compared to regular OpenCPP coverage is 10 to 100 times faster. However, the performance still degrades with the number of sources, and whilst those figures are far more attractive than regular OpenCPP coverage, we still require some unrelated optimizations to bring the performance at near parity to having no instrumentation. In addition to these raw performance boosts of the modified instrumentation compared to OpenCPP coverage, we also get some bonus optimizations of fast test impact analysis compared to regular test impact analysis. With optimized builds, such as the profile builds that we build our test targets in O3DE for use in automated testing, the compiler has the opportunity to optimize away any dead code and irrelevant dependencies. This, in turn, results in build targets built from less sources. And as we have seen, less sources means improved performance. What makes this bonus optimization particularly attractive is that it comes for free. We don't have to do anything other than change the build configuration of the targets we wish to build. As soon as we turn on compiler optimizations, we instantly get a boost in performance. And this performance is in the form of more accurate test selection. This would be functionally impossible to do with static analysis of the build system as we saw in the previous slide, even if we put aside the fact that they cannot discover runtime dependencies. Let's now see how test selection works for fast test impact analysis but using an optimized build, such as the profile builds that we use in O3DE for automated testing. As with before, the white circle represents all of the tests in the codebase. The red circle represents the actual relevant subset of tests selected for a given set of incoming source changes. The yellow circle represents the approximate subset of tests we've deemed relevant for the same set of incoming source changes. However, this is for a debug build. The blue circle represents the approximate relevant subset of tests for the same set of incoming source changes, albeit for a profile build. As we can see, the blue circle is still larger than the red circle, but is also significantly smaller than the yellow circle, and again vastly smaller than the white circle. This all comes for free by simply changing the build configuration. We've had to do no extra work for the algorithm. This all comes priced in for free with fast test impact analysis. Our provisional results are showing that on average 85% of C++ test targets are being rejected for incoming source changes that have resulted in on average, approximately 5 times speed up compared to running all of the tests in automated testing. There's still a lot of room for improvement here, and we have many ideas and future performance optimizations on the roadmap. Our end goal is a rejection rate of 95% or greater, and expect to see an overall speed up of 15 to 25 times that of running all of the tests without fast test impact analysis. Here we can see the time spent in automated testing using fast test impact analysis for approximately 130 pull requests waiting to be merged into the O3DE codebase. The orange line represents the average duration for the C++ tests spent in automated testing and sits at about 35 seconds. Notice that the vast majority of pull requests actually spend significantly less than 35 seconds using fast test impact analysis. These PR builds are taking just a few seconds to complete. However, the average is still being dragged up in duration by the PR builds that are taking significantly longer than the average to complete. These PR builds just happen to pull in particular test targets that take in the order of a few minutes to complete. This is one of the shortcomings not just of fast test impact analysis, but test impact analysis in general, where you will only ever be as fast as your slowest test. That is to say, if you had, say, 100 test targets, of which 99 of those test targets took a few milliseconds to complete, but one of those test targets took 10 minutes to complete, it doesn't matter if you manage to reject 99% of those test targets. If you happen to pull in that one test target that takes 10 minutes, your duration for that PR build will still be 10 minutes. It should be pointed out that although test rejection rates strongly correlate with shorter durations, you cannot assume that simply rejecting tests will automatically lead to shorter durations. In this graph, we can see the C++ test rejection efficiency of the same PR builds as the previous. As with the previous graph, the orange line represents the average rejection efficiency, which stands at approximately 85%. That is to say, for each PR build, approximately 85% of tests are being rejected. You will notice again that the vast majority of PR builds are actually operating at an efficiency well above the average. In this instance, our long pole PR builds are PR builds where the fast test impact analysis algorithm is pulling in significantly more tests than the average. This occurs when upstream dependencies with a large volume of downstream dependers have their sources changed. For example, AZ core is a build target which a lot of other build targets depend on. If we are to modify sources in AZ core, we will expect to see significantly more tests being pulled in due to all of the downstream production targets depending on AZ core, and thus all of the test targets that are dependent on those production targets being selected for the run. This is a drawback of the fast test impact analysis algorithm, as it is very sensitive to upstream dependency changes that have a lot of downstream dependers. This is due to the fact that the approximation of coverage, and therefore the approximation of test selection, becomes less and less accurate the further away the changes are to the impacted build targets. Future work will involve implementing another newly designed algorithm called sparse test impact analysis. Sparse test impact analysis attempts to bridge the gap between fast test impact analysis and regular test impact analysis. It achieves this by having a much more malleable concept of coverage. For example, it will use fast impact analysis to lay down that rough approximation of coverage data, and then slowly over time it will attempt to incrementally shrink that gap between the approximation of the coverage and the true coverage using a few newly developed techniques. This will allow sparse test impact analysis to deliver all of the performance of fast test impact analysis whilst having the high resolution coverage data of regular test impact analysis. The goal of sparse test impact analysis is to shrink that blue circle we saw in the previous diagrams over time to become closer and closer to the red circle with each run of automated testing.